Okay, so let's look at a little bit more about El Nino and Southern Oscillation. Note that suddenly I started talking about ENSO. So the El Nino was the terminology from the Spanish colonizers in South America that we mentioned. Southern Oscillation was the name given by Sir Gilbert Walker, based on his Darwin-Tahiti pressure oscillation. And Jakob Bjerknes showed that they are the same thing. So at some point in the late 80s, early 90s, I think, El Nino began to be called El Nino Southern Oscillation, because now you can talk about the warm phase of Enso and the cold phase of Enso as El Nino and La Nina. Enso is not as evocative as El Nino or La Nina, but scientifically it becomes easier to just talk about ENSO. Okay, so we looked at this kind of a plot before. This is now showing the mean sea surface temperature in a box in the deep tropical Pacific, around which the deviations are measured. And looking for about 100 years, you can see that there are El Ninos and there are La Ninas. This is not using the red and blue colors, but you get the idea. And if you look at this way, where the climatology, the background state, is computed as a mean of the whole period of 1900 to 2000, and you will tend to think that maybe this period had fewer El Ninos and more La Ninas. In fact, this was interpreted as the impact of global warming on El Nino. Right? Global warming is quite important, and it's impacting so many aspects of human life and other species as well. So obviously this got some attention, especially this so-called long El Nino from 1991 through 1994 or so. And immediately there was a debate about whether that's really global warming and whether there is really a change in the number of El Ninos and La Ninas. So this change in the number of El Ninos and La Ninas from decade to decade is often called Enso variability. So El Nino is climate variability, and Enso variability means the change in the El Nino itself. Okay, so this paper simply took the climatology as not the mean for the whole period as is done here, but as some kind of a 10-year running average. If you don't know what that means, basically you have a time series and you start with year 1 to 10, you take the average of that, you move the window by 1 year, and you go from year 2 to 11, 3 to 12, and so on, and you get this kind of a wavy climatology where the climatology is not stationary anymore. As we said, there is no clear definition of climatology. We say 30 years, but that's not based on any kind of dynamics or physics, right? So you can do anything you want. But for practical demonstration of this idea, this is an excellent way to show it. And when you look at the deviations of warm and cold phases of ENSO from this non-stationary climatology that is changing every 10 years or so, then you can see that this stark contrast of no El Ninos and a lot of La Ninas basically disappears, and the entire period looks like there were El Ninos and La Ninas throughout. And of course you have strong El Ninos here. Okay, and there is also some arguments that the global warming picked up around the mid-1970s, and you can see that the climatology here is warmer than the previous periods. But remembering that the El Nino itself redistributes the warm water, and the global mean temperature actually goes up by a tiny bit during an El Nino because the ocean is releasing the stored up heat into the atmosphere. So you can think of it as a mini global warming. The climatology shifts and then El Nino changes, or does El Nino itself change the climatology? These kind of questions are not very easily answered, but what we can do is continue to monitor the impacts of El Nino on other features like the monsoon. I'll come back to this on a podcast on the monsoon itself. What it is doing here is showing again a deviation of the all India rainfall. So you average the rainfall over all of India and call it all India monsoon rainfall for June, July, August, September, which is the rainy season. So for each year there is one bar here, and again the deviations are from the long-term mean as below the long-term average or the long-term above the long-term average. And these star blue and red circles or circles on the certain bars here are the El Nino when it's drier and La Nina when it's wetter. The point of this here is that there are many years where there are excess rainfall during a season, but it's not a La Nina. So only about 50% of the wet years are explained by La Nina. And similarly, there are many drought years which are not related to an El Nino. So here we can argue that only 50% of the droughts are actually explained by El Nino. And the trick here is that the monsoon is happening in June, July, August, during which time El Nino is still evolving. And El Nino peaks in December, January, February, 6 months after the monsoon. So is the monsoon being affected by El Nino, or is monsoon somehow affecting the El Nino? Remember that the monsoon is also a strong heat source. So is it possible that the monsoon can affect the El Nino? So these are also open questions that are not easily answered. And this is the asymmetry that I mentioned, where you can see that this is looking at the Nino 3 index, Nino 3.4 index, which is the sea surface temperature anomaly averaged between something like 90 west and 150 west, 5 south and 5 north. You can look it up, and it is looking at La Ninas, which are blue, and El Ninos, which are red, from 1948 through 2008, and it argues as to why you can have La Nina lasting for multiple years, whereas El Ninos typically die away in 1 or 2 years. Okay, so there is that asymmetry as well. So El Nino is a lot is known about El Nino, and a lot still remains to be known. And the other big question is how El Nino has changed over long times. Okay, this is a map of the sea surface temperature with our upwelling mean sea surface temperature, upwelling here, and the warm pool over here, the ITCZ and the SPCZ clearly show up, and then there is the net surface heat flux, with the convention that when the heat flux goes into the ocean, it's positive. We have already talked about how upwelling brings up cold water, and the ocean and the atmosphere tries to damp the cooling by putting order 100 watts per meter squared into the ocean, whereas the western boundary currents bring up warm tropical waters into these mid latitudes, and the atmosphere is colder and is picking up the and the atmosphere is picking up the heat from the ocean. So a cute way of thinking about this was proposed by George Philander, again along with his colleague Alexei Fedorov, who is now at Yale University. George was at Princeton. I think he's retired now, nonetheless. They said how much heat gets taken up here depends on how shallow the thermocline is. If the thermocline is shallow, then cold waters occur easily with upwelling, and ocean takes up the heat, and that heat is lost mostly here as well as here. So there is a kind of a global balance of heat uptake and heat loss. So if you change the thermocline depth here, the heat flux would change, and this heat flux would also change. Or if you had some processes which were changing the heat loss here, then the thermocline here would have to adjust to reflect the heat flux perturbations here. It's a kind of a heuristic argument because the time scales of when at which this can happen is not always very obvious, but nonetheless we know that the waters circulate from here to there and then back at some time scales in the shallow circulation versus the deep circulation and so on. So these are looked at even on long time scales using these ocean sediment data from these blue dots that are noted here. Ocean sediments, we'll see a little bit later on, have signatures of biological production at the surface, for example, which allows us to estimate past temperatures and past productivities. In other words, the strength of the upwelling winds and maybe El Nino in the past, okay, or at least the temperature gradient in the past. Has this temperature gradient always been so strong, or has it changed in the past? If so, what are the processes that caused it, and what other changes would have occurred if you somehow changed this sea surface temperature gradient in the tropical Pacific, okay? And the contrast is fairly obvious here. The Pacific is really huge compared to the Atlantic and Indian Oceans, which also matters for the El Nino-like behavior in the Atlantic and Indian Oceans. Okay, so that's a fairly long podcast, so I'll stop it there, and then we'll make a few more points about El Nino and global warming. Okay.